Hi kids, it's Mr. Erik with another science quiz for you. Today we're going to interview Dr. Kevin Reiter. He is a chemist that works at the Karlsruhe Institute of Technology in Germany. Hello, Dr. Reiter. How are you doing?
I'm fine. How are you?
Good. So you're a chemist. Could you please explain what a chemist does and what they research mostly?
Okay. Yeah. So as you just said, I'm a chemist since I studied chemistry. But you probably also know that there are many different areas of chemistry. So, for example, there's organic chemistry and inorganic chemistry, which mainly focus on the synthesis of new structures and molecules. And there's also, for example, polymer chemistry with a focus on plastics and all kinds of rubbers and stuff like this. And otherwise, we have the area of biochemistry, as an interface between biology and chemistry. And during my master's degree, I specialized in the field of physical chemistry. And this area is more physically and mathematically oriented and serves to better understand and describe ongoing chemical processes. And to be more precise, I then even delve further into theoretical chemistry. And in this field, or this is a field of computer science in which calculations and simulations of chemical systems are carried out on a computer. And this allows processes to be simulated or properties of molecules to be calculated.
Are you a theoretical chemist?
Sorry?
Do you research theoretical chemistry, or
exactly?
Yeah?
This is what I specialize in. Theoretical chemistry, and these theoretical results can then be compared with the experiment and provide additional information. So even though I'm a chemist, I haven't seen the lab from the inside for a long time now.
So it's a lot of mathematics, right?
That's true, yeah.
Yes, yeah. So when you were studying to become a chemist, what was your everyday life like in terms of your career, actually? Like, what did you do, like, in the research, like?
So I would say there are basically two types of theoretical chemists. Some are pure users of computer programs and carry out these calculations, and the other are kind of program and method developers and program most of the time. But the last group usually also applies their own methods. And I belong to the latter, and so I spend most of my time programming. And in my area, quantum mechanics is the basis of these type of calculations for any kind of molecular properties. So some of these are based on very complex mathematical equations, as you just said, and they have to be programmed for these calculations. But often you also spend a lot of time trying to find bugs in your program code, which is probably the daily work of a programmer in general. You always introduce some bugs into your program code, and you have to find them.
So my question is, the theoretical chemistry, in what real-world situation is it used for example? Like, what situation would you need a theoretical chemist? Like, could you explain that?
During my PhD thesis, I worked in the field of the calculation of so-called nuclear magnetic resonance spectroscopy, so NMR spectroscopy. And NMR spectroscopy is widely used method for the characterizing and elucidating of structure of compounds. And so let me just show you a simple example.
So this is a method for looking at the nuclear structure of materials, correct?
Exactly, yeah, that's true. So if we have this simple molecule right here, which is ethanol, which is just a regular alcohol you find in all your drinks. And if we take a look on the spectrum of this compound, you see the result on the right side. So there are basically three different signals just ignore the fact there are several lines per signal, so we only concentrate on these three different types of signals.
I should also explain to kids that what we're looking at is the elemental structure of ethanol, right?
Exactly. Yeah.
So you see kids, you can see that there's hydrogen and carbon. What is OH again? Oxygen?
It's oxygen. Yeah.
Oxygen, yeah.
Yeah. So the gray atoms are carbon atoms, white is hydrogen atoms, and red is oxygen. And this is a spectrum for hydrogen atoms. And three different groups of signals you can see in the spectrum correspond to the different groups in the molecule. For every different molecule, you get a different spectrum, and this is how you can, in principle, investigate the structure of the molecule you're looking at.
So I would say this is almost exactly pure science compared to some of the other sciences out there, because it's definitely looking at the structure of an element or an actual material, you know. So you're looking at a pure science that other scientists can use in their research as well, the information that you're gathering, right?
Exactly, that's true.
That was an earful, kids, right? So as you can see, it's very based on mathematics and on pure science. So do you have any interesting stories about your work in the lab that would be interesting for kids to hear about?
Yes, probably an interesting project I was involved is related to cryptography.
Cryptography.
Exactly, yeah. So I guess nowadays it's more important than ever to exchange data securely without it falling into the wrong hands. And usually a key is required for any kind of encryption.
Let me explain one more time to the kids. So cryptography and encryption has to do with exchanging information, usually over the computer, right? Over the computer, right? With sometimes organizations or businesses want to exchange information with other employees, for example, and they don't want to have people stealing it. It's a way of encrypting, making it impossible for other people to actually open it or look at it without having a special key, for example, or something like that, right? So that's what you're talking about right now, right?
Exactly. And here was the idea of hiding the key in form of a molecule. And imagine there is a large molecule that is built from 4 different smaller molecules. So for example, if we combine a molecule A with another molecule B, C, and D, and if there are now, let's say, 50 options for the molecule of type A and B and C and D, for example, this leads to 50 times 50 times 50 times 50, which is more than 6 million combinations for such a molecule.
That is unbelievable, what you just described right there. So,
exactly. So you're not really encrypting the message itself in the molecular structure, but you are providing the key for the recipient so that it can decrypt the message.
It's so X-Files, it's not even funny.
Yeah. So, and for example, this key in the form of a molecule can then be dissolved in liquid, for example, and the recipient then only has to extract the molecule from the liquid and determine its structure.
Kids, did you understand that? You can now send messages encrypted in water, for example, to other people. So that's very interesting, actually. That's almost like the future, right? The future of like spies or something like that, you know, if you want to think about that. It's kind of very interesting. So thank you for presenting all this to us. My last question, of course, is, as usual, what kind of advice would you give to a child or a kid who's interested in pursuing chemistry in the future or being a chemist?
Well, so generally I would say stay curious. Science thrives on curiosity. To talk explicitly about chemistry in general, I would say to study chemistry is very time consuming because you have a lot of lab courses. and you should also have at least some interest and understanding of mathematics and physics. It's not, yeah, you don't have to be perfect in this science, but
especially for chemistry and things that require such mathematical concepts, you should have some kind of, you should find it at least interesting, right?
exactly, yeah. And this is a particularly important if, like me, you want to delve deeper into physical chemistry and more precisely into theoretical chemistry.
Thank you very much, Dr. Reiter, and thank you for letting us know about chemistry. Thank you.
Thank you.
And good luck with your future endeavors.